Hello and welcome back to another lecture. In this lecture we're going to talk about pre-stressing. What I'm going to do in this example, we're going to go ahead, we have this pre-stress beam is 64 feet long, and this is the cross section. I'd like to find out what is the stress at the bottom and top of this pre-stressed concrete beam. But before I do that, I want to explain to you how we have these formula for pre-stress at the bottom and pre-stress at the top. So you need to understand this concept, understand the concept where these formula came from. So if I look at this, say this was a beam, not a pre-stress beam, just a regular beam, and we put it, this beam right here, we put it under the service load of dead load and life load. And what happened, the beam kind of bends. Normally when you have a beam like this, you have stress on it. There are about 6-7 type of stress. But there's one stress is more dominant, and that's a bending stress. And if this is a center our shape, not this shape, say if we have a shape like square shape, and that's the center of it, the stresses caused by the bending stress, we all know the bending moment causes bending stress, F of B, which is equal MC over I. And C is basically the distance from here to here, that's a C, and this is also a C. C at top, C at bottom. Now, this simply supported beam with this type of load is going to cause a bending stress. Bending stress is going to be, this is be the neutral axis, center of our shape. It's going to be like that and going across. And we're going to say this is a compression and this is a tension. If we say compression is a negative and tension is a positive, we use that every time we do analysis. The stress distribution on a simply supported beam could be timber, steel, and non-pre-stressed concrete. It's just basically you have a compression and tension, and assuming the neutral, like for this example, assuming the neutral axis is at the center of the beam, and you end up with the stress distribution like this: compression on top, tension on bottom. And if we say tension is positive, compression is negative. However, in concrete, we know concrete is about 10 times stronger in compression than tension. That's why we have reinforced concrete. We put a reinforced bar at the bottom to make up for the weakness in the tension. But in pre-stress, they came up and said, what if now if we induce compression into the beam itself? That way, it will reduce the tension in the concrete, and we'll be good. And it's very successful, and you can basically increase the span of the beam by quite a bit, going from 30 feet to 60 feet or plus. So what happened, there's two different ways they can do this, by pre-tension and post-tensioning. In pre-tension, they bring in these wire strength, and they put them in a beam, and while it's inside the foam, they stretch the strands and pour the concrete. Once the concrete is cured to a certain allowable stress, then they let it go. And then that will create compression into the beam itself. So it's going to be like you have compression induced into it, as I show on the screen over here. And this, because it's created a compression, now you have a compression like this added to the beam. And that's compression, so again, it's negative. However, they don't put the strand rod down the center, because that might cause some issue. What if we just move it down a little bit at the bottom? You get the best benefit out of it. And if you do that, then you have a distance here between the center of the beam, or neutral axis. They call that E, and that's going to cause another stress. Eccentricity causes the bending moment upward in the beam, and therefore causes compression at the bottom of the beam. That way, we end up with another stress, which is going to be, use a different color here. and it's going to cause compression at the bottom, tension at the top. This is going to be positive, this is going to be negative. And of course, when you put all this together, you end up with this result right here. That's how we got it. And when we calculate that the stress at the bottom at the top of a prestressed concrete, and we have to know these, that's where they come from. All right, so I'm going to erase this, and we're going to go ahead and proceed with this problem. And of course, this will be our first lecture, and we will continue with more. Look at the problem with the specification is given to solve to find the stress at the bottom and the top. So we're going to find the stress at the bottom at the top once this beam is made and it's in a form, and they take it out, it's cured, and they make these about probably they have this like a runway about 400 or 500 feet long, and they make about 6 or 7 of these at the same time. And then when it's done, they take them out of the form. When it's cured, they move them over to the yard, and we want to measure the stress once it's in a yard, initially, before it loses any pre-stressing. Then we're going to do final stress at the top and the bottom when it's at the job site and it's at the service load. So the information is given is basically the 64 feet long, and this is the cross section, and we have a S bottom, S top, and this is a neutral axis right here, and your C top is about 623, and the C bottom is 17.77, and there's a 10 half-inch diameter 7-wire strand, which is the first thing we're going to do is find the area of pre-stressing steel. Strength area, we have 10 of those, and each one of those, the half-inch, the area is about 0.153 inch square, and that is the area of the pre-stressing steel. And then the PI, which is basically the initial pre-stressing force, and that was given as, and we learned that from 1,000 years ago, that stress is equal P over A, and if you use that equation, then you're going to say that okay, PI is equal APS time F of PI, which that is equal 1.53, multiply that by F of PI given to us is 189,000 PSI, which is basically 70% of the FAU, and FAU is 270,000 PSI. So this comes out to be 289,000 and 170 pound. Looking for is a PE, which is effective pre-stressing after the losses. We talk about losses in future lectures, and that is given to us by APS time the stress of the after losses, which is given in a problem. In this situation is what comes out to 1.53 times 150,000 psi, and that is 229,500 pound. Beam. W of the beam is given as 359. Let me double check that. The weight of the beam is 359 pound per foot. So again, we are going to go ahead calculate the bending moment just due to the weight of the beam itself. And for uniformly distributed load, bending moment is WL squared divided by 8, which is equal 359 times 64 square, and divide that by 8. Let's multiply by 12 to make it an inch pound. Comes out to 2,205,696 inch pound. So let's rewrite this top formula in terms of radius of gyration and section modules. Basically, and that is can be written. So I'm going to go ahead and just rewrite this f a top based on radius gyration and section module, and this is the formula for it. And let's plug it in. And initial pre-stressing came out 289, so that's minus 289,170 divided by the area of concrete, which is 449, time 1 minus E was given to us as 1477 time C at top was 623 and divided by radius gyration was given to us in a problem as 5004. And that's squared. Let me double check that. No. So R squared was given to us as 5004. There we go. Then minus MD came out to 2,205,696, and divide that by S as the top, 3607, which is equal minus 70 psi, which is in compression. So we did the top initial before pre-stressing loss. I mean, when they took the double T out and moved in a stockpile in a yard, and that is the stress at the top of the beam. So let's calculate the stress at the bottom. So the stress at the bottom, rewriting it, this is the equation for it. So F of bottom is equal minus PI, it's the same number, 289,170 divided by the area, 449, time 1 plus E came out to was given as 1477, and C at bottom was calculated at 1777, and divide the whole thing by radius of gyration, which is 5004, and plus the MD, which was 2,205,696, divide that by S at bottom, which is 1264. So F at bottom comes out to minus 2277, 2,277 psi, and that is in compression. The problem, the specification, we looked at it, it was given to us that, so now this is the stress at the bottom at the initial, and per spec, it cannot be more than 2,880, which is the maximum allowable stress in a concrete at the initial pre-stressing, which is basically 60% of the concrete at the initial pre-stress. So this number is less than 2880, which checks out, it's okay. So now we calculate the stress at the bottom, at the top of the beam at the initial pre-stressing before it's moved out of the factory to the job site. Now let's do the calculated. Once it's at the service load, we put the life load and dead load on top of it, see how it's going to be. Now we're going to go ahead and continue with this. We're going to calculate the stress at the final condition at the service load. Once the concrete is at site and it's set and it's loaded. And first we're going to find the bending moment for everything. So we have a moment. This is the dead load and live load came out to 420 pounds. So moment for dead load and live load comes out to dead load, live load, MWL square divided by 8 for uniformly distributed load, simply supported, and that comes out to 420 times 64 square divided by 8, multiplied by 12, make it an inch pound, 2,580,480 inch pound. Now our M total comes out MD plus MDL, and that was 2,580,480, and I erased it. It was 2,205,696, and that will give me 4,786,176 inch pound. So the stress at the top become the PE, which is, so the stress at the top become PE, which is a pre-stressing stress after losses. And that came out to be, was given, which I erased the board, 229,500 and divided by 449 time 1 minus E came out to 1477 time S at top, which is 623 divided by R square, which was 5004, and 4, 7, 8. 786, 176 divided by 3,607, and that comes out to minus 889 psi. So it comes down to 898 psi in compression, and based on the spec, the code, that has to be less than 45% of the maximum allowable compressive stress in concrete at service load, which comes out to less than 0.45 of 6,000, and that is equal 2,700. And it is, so that checks out. We're going to go ahead and do the bottom. Time 1 plus E was 1477. C bottom came out to 1777. Divide that by our radius gyration square, 5004. Then plus M total, which was 4,786,176. Divide that by the S at bottom, 1264. So that comes out to plus 594. That means it's in tension. Less than maximum allowable tensile stress in a concrete at the time of service load, which is basically the has to be 594, has to be less than, and that is the equation for that is 12 square root f prime c, which is equal 930. That's less than that. It checks out. See how we check the stress at the bottom and the top of the pre-stress beam after being cured at the supplier yard. So before its losses and after the losses at this final service load, we check like that. Hope this was useful. Give it a thumbs up if you like.